Hello, it's Stat135, Lecture 35. So we've been talking about simple linear regression for a while now. Last time we discussed the 95% CI for beta 1 and also for beta 0. For beta 1, it's centered at beta 1 hat plus or minus the t statistic at alpha over 2 times the standard error for beta 1 hat. So the standard error for beta 1 hat squared is the RSS, the residual sum of squares, divided by n minus 2 times n variance x. So the topics today are not in your book, but they're very standard and very important. So the first one is about the SE of the regression line itself, not just the regression coefficients. The second is a confidence interval for the Tyche line. We'll see that the regression line is an unbiased estimator of the Tyche line. And lastly, we'll talk about a Bayesian topic, namely prediction intervals for a new observation. So SE of the regression line. So let x be a point on the x-axis. If y is paired with x, then we can write y using our statistical model as beta 0 plus beta 1 x plus e. Notice that e there, that's the random part of the right-hand side of the equation. And so it says that all the points don't need to lie on the Tyche line. If we take the conditional expectation with respect to x is x, we get beta 0 plus beta 1x. So the conditional expectation lies on the Tyche line. We denote x on the regression line by y hat. And so a picture is as shown here. We have the Tyche line and the regression line both above x, and we can see here by taking the conditional expectation of y hat that we get the Tyche line. So right, so we get the so we get the result that the that y hat is an unbiased estimator of the conditional expectation of y given x is x. And well, technically I should say the conditional, so y hat conditioned on x is x. So y hat is y bar plus beta 1 hat x minus x bar. That's just follows from the definitions. And we can take the variance of both sides, and we get the variance of y hat is the variance of y bar plus x minus x bar squared variance of beta 1 hat, and then a covariance term that turns out to be 0 as I show below here. So the variance of y hat here is sigma squared over n plus x minus x bar squared sigma squared over n variance x. And just rewriting that, you get the highlighted equation below. We don't know what sigma squared is, so we can approximate it by s squared, which is the RSS over n minus 2. So here's a picture of what we have. So I've drawn basically the error curve for each value of x. Notice that the error is smallest when x is x bar, So through the point of centers, you should have the smallest. Error, and great. So the error bars are sort of centered around the regression line, and there's a 95% chance that your interval contains the conditional expectation of y given x at that whatever x value you're looking at. So more formally, the confidence interval for the Tyche line is as shown here. We have y hat plus or minus tn minus 2 alpha over 2 times the standard error for y hat, where the standard error for y hat here is as shown. It's what we just derived. So next we're going to talk about prediction interval for a new observation yn plus 1. This is a very Bayesian topic, since what we have now, yn plus 1, is a random variable, and a confidence interval for a confidence interval for a random variable is called a prediction interval. So a new observation yn plus 1 is a random variable. So you give you give a new observation xn plus 1, and you get out a new response. So we're going to find a 95% pi for yn plus 1. Okay, and so we have this theorem, a 95% pi for a new observation yn plus 1 for predictor xn plus 1 is given by the formula here. And so notice that this essentially looks the same as before, except that now we have y hat n plus 1 instead of y hat, and our standard error is a bit larger. Notice the 1 in it. So there is more uncertainty here. And so I've sort of drawn the picture of the prediction interval, and it's a little bit wider, as you can tell with the purple dotted line here. And this is for a new observation. So we're going to prove this result. So when yn plus 1 is a new response, not used in the calculation of the regression line, it's independent of the regression line, of the predicted value of the regression line at above xn plus 1. So consequently, the variance of the residual e hat n plus 1 is larger than the variance of the residual ei for I between 1 and n. So we're going to make that very clear below. So here's essentially the picture of what we have, and you can compute the variance of en plus 1 hat, and by definition it'll be the variance of yn plus 1 plus the variance of y hat n plus 1, and right away so yn plus 1 and y hat n plus 1 are independent, because the y hat n plus 1 was calculated with our old data, which involved the xi, yi's from 1 to n, and xn plus 1, the yn plus 1 is not dependent on our old data. So oh, I'm sorry. So the yn plus 1 hat is not dependent on xn plus 1. So anyway, these are independent, and so the variance just goes across the sum, it distributes, and we get the equation that we need here. And furthermore, we have the expectation of the residual here, e hat n plus 1, is 0 here. So we calculate that and show that. So the residual is normal, and its mean is 0, and we've calculated its variance. So so we get a t distribution with n minus 2 degrees of freedom, and hence we get the formula for the prediction interval as shown here. So again, it's n minus 2 degrees of freedom because our y hat is only using our old data. Great. So next time we're going to discuss the F statistic for regression and we'll see how regression what regression has to do with ANOVA next time. See you.